So thanks so much for the invitation. Thanks to the organizers for organizing such a nice little community event with everybody coming. So I'm going to be talking about neural networks in the limit of infinite depth and width. So to start with, let me tell you the main idea of the talk is somewhat obscured by Zoom. Okay, we're going to approximate neural networks by thinking of what happens in the limit as the number of neurons goes to infinity. So instead of thinking of a neural network as some system with 1,000 neurons, we're going to think of it as having infinitely many neurons and say what happens. This is a little bit like in statistical physics. If you have a cup of coffee, you don't think of it as something with 10 to the 50 molecules. You say this is some continuum. We took the limit and we can do fluid mechanics and PDEs. So here's the picture. So I have my neural network, n neurons in every single hidden layer. So n is in red, n stands for number. It's the number of neurons. It stands for neurons, that's better. Okay, it stands for the number of neurons in each hidden layer. And L stands for layer. That is what layer you're in, the depth, how far in you are into the network. And we're going to take this, we're going to imagine this picture getting more and more zoomed out and more neurons appearing and say what happens. Okay, but this is the problem with infinite limits, is that there's more than one way to do it. And so one common way is to do the infinite width limit, which in our language would be n goes to infinity and L is constant. So you would fix L and you imagine in every single layer it's getting wider and wider, those each individually going to infinity. Some people call this the neural tangent kernel limit. Okay? And there's a nice theory, this thing called the neural tangent kernel. In some sense, in this limit, this whole neural network becomes a kernel machine. And you can say what everything the kernel is doing just in terms of this kernel, this neural tangent kernel. But the problem is that this neural tangent kernel sort of loses some of the magic of neural networks. So for example, it cannot learn features, So somehow it doesn't adapt itself to the data in the way that you would like. It cannot learn features. So this is a bit like the kernel in the previous talk. In contrast to this infinite width limit, what I'm going to tell you about today is some of my work on an alternative limit, the infinite depth and width limit. And in this infinite depth and width limit, we take n to infinity and L to infinity at the same time so that their ratio is order 1. So you can think about that instead of sort of stretching out the n and making it really wide in this direction, I'm sort of zooming out equally in both directions. And as I zoom out, I get a picture of a neural network that has a fixed aspect ratio. So maybe it's 2 to 1 or 1 to 1. And as I zoom out, it gets bigger, both in terms of width and depth. And we'll see that this is a lot more complicated of a limit. So there is no analog of the neural tangent kernel. I cannot tell you what training does here. So this one is still quite open, question marks. What does it do? But I'll tell you 2 nice stories about it. When I was presenting this work at NeurIPS, I was at the poster defending my infinite depth and width limit stuff. And someone said, does that mean that the infinite width limit, the neural tangent kernel, is wrong? They came up to me and said, is it wrong? Are you starting a fight here? And I'm going to tell you, I'm not starting a fight. So I came up with this great analogy to tell you what is the relationship between these 2 things. And here is the analogy. I want you to imagine you're in 18th century France, and you're interested not in neural networks, they haven't been invented yet, but you're interested in coin flips. Okay? So instead of looking at neural networks, you're looking at sequences of coin flips. You have n coin flips, and you're like doing math with your n coin flips. There's some gambling game where you have to flip 50 coin flips. So you have 2 parameters. You have n, the number of coins, and p, the probability of heads. And you're interested in counting the number of heads, and you're doing math. And your friend Carl comes up to you, and he says, I have this brilliant idea. I can take this mathematical limit, n goes to infinity. I guess maybe I should include Carl Demoivre and some other people. But okay, Carl, he does the limit as n goes to infinity with p constant, and he gets this beautiful shape, the Gaussian limit. Right? And he answers all sorts of questions for you. All the questions you're doing with coin flips before, like working with binomial coefficients and slaving away, are answered by this beautiful purple curve. Right? But then one day, your friend Simeon comes to you and says, I'm doing this other one where we flip 50 coins, but there's only like 2 or 3 coins that come up heads usually. And it turns out he's working in this other regime, the infinite odds in coins limit, where the odds of any individual coin is going to infinity, scaled with the number of coin flips total. So n is going to infinity, p is going to 0 in this balanced way, where n times p is some order 1 constant. And of course, if you've taken the classical probability course, you know we're no longer in the Gaussian limit. We're inside the Poisson limit, and it's very different. Okay, so now somebody comes to you, you're defending your poster at NeurIPS 1755, and someone says, is the Gaussian limit wrong? Are you starting a fight with Carl? You say, no, it's just different. Okay, look, sometimes you're in this regime, and this is the right thing. Sometimes you're in this regime, and this is the right thing. And that's exactly what I'm going to try to show you today. So I'll show you some ways in which they're different. And we don't know everything about the one I'm going to talk about, the infinite depth and width. So there's still many open questions here, but there are some important ways when you're in this regime, you get something very different in the map sheet. Question here.
Does it ever make sense to take infinite depth and width?
Yeah, in some sense, no. Yeah, so then you get an infinitely skinny network, and somehow it's like optimally bad. So, yeah, yes. Okay, more on that later. Okay, yeah, you'll see why. You'll see why if L over N goes to infinity, something bad happens.
So a similar question.
Yeah.
Here you assume that L over N is all flat.
Yes.
But when you look at like graph properties,
right.
and we compare the ratio of edges and the number of nodes,
right.
we not necessarily have the ratio being 1. We
yeah.
can talk about other ratios. And you have different phenomena when the ratios are different. So do you also consider other ratio, or this is just first?
I guess this is the first step, L over N, and you're going to see exactly how L over N appears. And so when L over N is going to 0, you're going to get one thing. When L over N is going to infinity, you're going to get another thing, and you'll see exactly how that appears. So for now, I want it to be order 1, and you're going to see precisely what happens at infinity and 0, which should cover some of the cases going faster or slower than. Yeah, great question.
Sorry, you really mean like data?
Yeah, okay, fine, yes. Okay, good. This is the beauty of having an iPad. Okay, did I fix it? Yeah, okay, okay. All right.
You can fix it on the screen.
Yeah, that's right. So I'm going to talk about 2 things very quickly. I'll just say the results without getting into too much detail. Phenomenon 1 is the marginal output distribution, and this is joint with Marginal, who's now at Princeton, his postdoc Mufan Lee, and Dan Roy, who's sitting in front of me. Mufan is on the job market, so if you have a job, you should hire him. He's quite good. Phenomenon number 2 is on angle degeneracy, and this is with my master's student, Dan Jacob, and also some stuff with Mufan Lee as well. Okay, so the first thing I want to tell you is about a very simple thing. Let's look at one point at a time, okay? So take a single input, x alpha, and put it into a properly initialized network. I'm not going to tell you what that means. You have to use your imagination. And we're just going to look in the Lth hidden layer. So look, L layer is the, that's some vector in Rn. And just on initialization, what is the distribution of that Lth hidden layer? Very simple question about a vector in Rn. And you, in the infinite width limit, you get a very simple answer. What is it doing? It is purely a Gaussian vector. So it's some vector whose entries are independent, IID, mean 0, variance 1. Very simple answer. We understand what that means. In the infinite depth and width limit, something different happens. You still have the same vector W, but now it's multiplied by this scalar. So you have this scalar, e to the 1/2 g. And the scalar multiplies every single entry of the vector by the same amount. So there's this one random scalar g that is either blowing up or shrinking the entire vector W. And this means the entries are no longer independent. So this is a very big difference in the infinite width limit. All the entries are independent. And over here, the entries are no longer independent because they're all linked by this scalar e to the 1/2 g. And what is g? G is itself a Gaussian. So you might recognize an exponential of a Gaussian. Sometimes people call that a log Gaussian or a log normal variable. And it depends, its variance depends on the ratio L over N. So the bigger you make the depth to width ratio, L over N, the more this is a huge variable that is very large or very small. And here's a simulation to show you what this looks like. You can easily see the difference by, instead of looking at the entire vector, look at the norm of the vector. And if you look at the norm of the vector, the infinite width limit predicts something that's not changing, whereas the infinite depth and width predicts that it gets more and more spread out. Here I've plotted the histogram of the log of the distribution. And in blue is the infinite width limit, which is always fixed, but the infinite depth and width limit is spreading out the wider, or the deeper you go into the network. So if you go 200 layers deep into a 100 wide network, you get this really spread out thing where there is some small probability of having either a huge vector, some tail over here, or some tail over here. So you might have a very big vector, a very small vector, and it could go either way. All right, that's the 1 point at a time. After you do 1 point at a time, what's the next natural thing to do? 2 points at a time. So let's feed, instead of feeding 1 point into our network, let's feed in 2 points into our network. So let's have 2 points, x alpha and x beta. And now we're going to look at the 2 vectors, fx alpha and fx beta. These should be in layer L. Let's add that in L. So in layer L. So in layer L, we have 2 vectors, both in Rn. And the very natural question is, what is the angle between these 2 vectors? Okay, that's going to be something between 0 and 2 pi. And here's a simulation of what it looks like. So here, I'm plotting it. It's just a simulation of what it looks like as you go through the network. So on the x-axis here is the layer number, what layer you're in, which number you're in. And over here is a representation of the 2 vectors. by projecting them down to a two-dimensional. They start out here and here. That's where the vectors started. And you can see that as you go deeper and deeper into the network, they get more and more smooshed together. The angle between the two vectors is going to 0. You can see that in the plot as well. So that somehow this neural network is having a problem of sending two different points to the same output. And of course, in the limit, this is a huge problem. Why do we care about this? If this angle is really small, then it's essentially saying your neural network is a constant function. It takes all the inputs and outputs them in the same direction to the same value. And that impedes training. So we even have a workshop paper where we have to ignore the purple vectors now. I'm scared to try to ask it to delete it. But so we have a workshop paper where we did, in CFAR10, we just trained some networks, and we compared the angle on initialization to the final test accuracy. And you can see it correlates quite well. So if you have this problem, it's on a log scale, so these negative numbers are very small angles, then you train quite badly. Whereas if you have something that is close to order 1, then you train no problem. Okay, and in more detail, we care about the rate at how fast this theta L goes to 0. And we have a nice paper where we tell you exactly how fast theta L goes to 0. And in fact, the way we do it, we don't do theta L, we do a little bait and switch here. We do the log of the sine squared of theta L, and that is going to, what is it going to? Good homework question for you. Minus infinity. Okay. So if theta is going to 0, the log of the sine squared is going to minus infinity. And there is a repeat of the same experiment I showed you before, but instead of doing it 1 time, I did it 10,000 times, and I drew a confidence interval. So you can see the angle is going to 0 very rapidly. The log of the sine squared of the angle is going down to minus infinity. And if you do the prediction, you say, what does the infinite width prediction do? The infinite width prediction is these green points over here, these green points. And those are not quite right. As you go deeper into the network, the infinite width prediction is wrong. You're sort of accumulating an error that gets worse and worse. And our theory is better. Our theory is better. And compared to the infinite width limit, which has subtracting a 2/3 pi theta, we have this little correction term, which is size 1 over n. And that little correction term is exactly the right thing to add to every single layer, so that as you add more and more layers, you don't sort of diverge exponentially.
How much it depends on your kind of unclear choice of ln sine squared of the. If I took another function of theta,
yeah,
would I get similar results?
Yes, that's a great question. We definitely did the log sine squared because that was the nice thing theoretically to get the nice curve. This is a good question. What would it be for something different? Because it's going to 0, the sine function is basically nothing. And so you could say we're just looking on a log scale. I'm confident I can reprove the same result on a log scale, but looking actually at theta instead of the log of theta, you'll get very different results because that sort of has a floor at 0 versus going off to minus infinity. Yeah, and actually for a while we were looking at the theta itself, and it's hard to prove things about theta because you get really close to 0, and it's hard to say. So the log, I think, is the right thing to look at. And that's going to minus infinity. Yeah, okay. So you have this small correction in every single layer, this little row n that we calculate, and it's roughly size 2 over n, and that's exactly the right thing to make things line up right. You might also ask a follow-up question, which is, okay, you have this little correction term, does it matter? We use a small correction term, who cares? And the difference is, without the correction term, it's going to 0 polynomially fast, like 1 over L, and with the correction, it's going exponentially fast. So this is like a qualitative difference between the two types of limits. Let me finish the talk, and then I'll do Akash's question here, since I'm out of time. So there's another thing you can ask is, what is the variance? And we have a much better prediction for the variance. The infinite width predicts 0 variance, because infinite width is based on a law of large numbers, whereas we can calculate the variance exactly. And that lets us not just get the mean, but a nice probability histogram of what is going on in any given layer. Okay. So in summary, what is different between the infinite width and the infinite depth and width is the infinite width is very useful. You can calculate all sorts of things, but the infinite depth and width can be more accurate for certain situations. So if the depth is comparable to the width, it's more accurate. You get things that are not Gaussian. You get things like log Gaussian, complicated things. And the theory on initialization is potentially useful for predicting results even after training, which is why it's interesting. We're also actively working on what happens beyond just initialization. Can you say something after training? That's work in progress. Okay, I'll stop there.
Thank you very much.
Thank you.
Yeah. This result of data, what was the distribution you used on XA and XB?
Oh, so it turns out it doesn't matter because once they go through the first layer on initialization, the only thing that matters is their norm. You put them through a Gaussian layer and they come out. It's a little bit like the random features thing from the previous talk. So yeah, so that's right. So it's whatever you start with is some initial value theta 0, and then our result tells you how do you update from one layer to the next layer. So you choose the XA and the XB that chooses theta 0, and then my result tells you how do you go from theta 0 to theta 1, from theta 1 to theta 2, and so on. So it's the initial condition on some update.
So if you let your input dimension also.
Yes, then you'll have some problem, which is that they'll go to 0. That would be theta equals pi. That would be theta not equals pi. They would start perpendicular. In high dimensions, they're perpendicular, and that would be a very valid theta 0 to start with. And we would still have the property that after many layers, they would go to 0. So even if they start perpendicular over many layers, they will tend to go to 0. Yeah, even in high dimensions. Let me see if I can find where I had the update rule. I feel like a woodpecker. Okay. So yeah, there's the infinite with update rule. This tells you how to go from one to the next, and there's our rule here. Let me move this. So it's really an update rule. You take the log of the sine squared of the previous layer, and then you modify it a little bit by adding on some stuff or subtracting it. Okay. Was there one other question? Yeah, in the back.
So why do we care about log sine squared in particular? Like, is that just like a constant away from ln of sine?
Yeah, ln of sine squared is exactly the same as ln of theta in this limit where theta is going to 0. And it turns out the sine squared comes out of a Cauchy-Binet identity. So we did it for convenience. It came out of the math. We got the sine squared through some determinant of the matrix. I'm confident it would be the same if it was the ln of theta. Yeah.
Okay, thank you.